Hi everyone, I'm part of Team 26 for Chemi 470, and today we're going to present our semester-long project about styrene production. So in today's presentation, we're going to talk about how we produce styrene and the process that we took to get from C4 raw material to styrene, and the economic analysis of our entire project. So our manufacturing plant will be built at Houston, Texas, because we have access of the pipeline of the raw materials coming from the olefin plant, and we also have ship channel in Houston, which would be beneficial for distributing our main product, styrene. And as you can see, our plant will be built to have 798 million pounds per year capacity. So now I'm going to pass it over to Shivam, and he's going to talk about reactants and the products for this unit.
So looking at this graph for the reactant cost, we can see the main contributors were the C4 and the acetonitrile, which gave the biggest numbers for the reactant cost. So looking at the products, the main product that we made was styrene, and we made a lot of money out of it. But as compared to the benzoic acid, which was a really low number, when comparing the reactant to the products, looking at this graph, we can see we actually made a profit. But when considering the other utilities and the other things that we used, and when added up to the reactant, you can see in the further slides that we actually had a loss. Now I'm going to hand over to Ivan, and he's going to talk about phase one, the process design.
So our process can be broken up into three phases: the feed purification, the styrene synthesis, and the product styrene purification. This is a block flow diagram of the first phase of our process, which is the feed purification. Our initial feed was a C4 mix with a butadiene concentration of approximately 50% by mass, which was too low for the reactor conditions, so we ran it through an LLE. The extract had 50% of our styrene from the initial feed, which needed further purification, and after a series of columns, the product from the columns was mixed with the LLE product, and the two streams were combined and fed to reactor 1. These streams had increased purity, and they reached about 90% butadiene, and were then fed to the reactor to begin production of styrene. The reactions of butadiene being converted all the way to styrene are going to be covered next, and I'll let Nick take over on that.
All right, so I'm going to go over phase two of the design process. So this involves the styrene production. So first off, we converted our butadiene that was purified from the C4 feed into vinyl cyclohexene. That was an intermediate, and that was done in reactor 1. From that, we took vinyl cyclohexene and converted to styrene in reactor 2, and that was our main product. So then the first part of phase 2 was the first reactor converting butadiene into vinyl cyclohexene. That was done through a series of intercooled reactors. So how we designed our reactors was we used space velocity data versus conversion of butadiene in order to design and acquire the amount of catalyst that we would need in our design process. When it came to our practical design, we realized that we had a very exothermic reaction and that cooling was an issue due to limits on cooling water. So in our final design, we ended up using a series of intercooled reactors. So what comes into our feed is our butadiene that we discussed earlier that was purified from the C4 feed. Here's our inlet conditions, and then we designed our reactor system to maximize the conversion of butadiene while also maximizing the selectivity to vinyl cyclohexene. The reaction of butadiene to vinyl cyclohexene produces an a side product, cyclooctane, but the selectivity to vinyl cyclohexene wasn't really an issue. It was a very highly selective reaction. Okay, so then I'm just going to go over how we designed our system in further detail. So we fit our kinetic parameters based off of the space velocity data provided, and we fit that in a single reactor with a linear temperature profile that met the specifications of a 25-degree temperature increase. So that can be seen in the blue. We fit an equation that set the conversion versus the reactor length, and we use this equation with an energy balance in order to design our series of reactors. So in the practical usage with the series reactors, we could take advantage of a higher temperature increase overall between the start and the finish. So because we ran at higher temperatures overall throughout the length of the reactor, we actually increased the reaction rate and increased the overall conversion, which can be seen in the orange, but it still followed the same profile. And then, like I just said, the temperature profile at various points within the reactor was higher than the overall design, which led to that overall higher conversion. So I'm going to let Anik take over and discuss how we converted our vinyl cyclohexene into styrene through the next point of the process.
So we have used a shell and tube reactor to convert vinyl cyclohexene to a styrene product. So it's 1-inch diameter tubes and 100 of them, and they are 7.5 feet long for this part of the production. So reactor size was dictated by the pressure drop and the cooling temperature limitation. So the temperature rise to the bed should be limited to 50 Fahrenheit because of runaway reactions, and also the pressure drop within the bed shouldn't be more than 15 psi to ensure good catalyst performance. So in our design, we only designed our reactor to have a pressure drop of 5 psi to have better catalyst performance. And then we use cooling tower water as utility, and then inlet temperature is 90 Fahrenheit and outlet is 110. We have also, as you can see, added steam and oxygen going into the reactor, and steam works as a heat sink for the very exothermic reaction that's happening within the reactor. And oxygen feed concentration was kept below flammability level, which is the 20% mole oxygen. And oxydehydroreactor performance are dependent on space velocity and operating condition. So as you can see, the pilot plant data that was given to us, the conversion with respect to temperature, and we have selected to run at 400 cubic feet per hour space velocity. And that gives us a nice conversion of vinyl cyclohexene to styrene within our reactor length, and we ended up getting very good conversion of vinyl cyclohexene to styrene. Now I'm going to introduce Ivan, and he's going to talk about the phase 3 of our process.
Phase 3 is the final phase of our process, and it involves the purification of our product, styrene. Styrene came out of reactor 2 at a low concentration, so it was important to concentrate it to the spec value. And this block flow diagram shows a summary of the process we took to purify the styrene product. As the diagram shows, we had the stream containing styrene fed to a series of parallel reactors. The two sets are C4A and C4B, and then C5A and C5B. The outlet streams for these reactors, C5A and C5B, in the bottom were our styrene product, which corresponds to S28 and S33. The net result of our styrene purity is summarized by these two pie charts. Our initial outlet from reactor 2 was only 24.2% by mass styrene, and our final product streams were 99.8% by mass styrene, which satisfies the specs. I'm going to next pass it on to Cody to go over more details on the purification process.
We met our styrene purification specification based on this series of distillation. The distillation series is designed to separate 4 main components. The first component being vinyl cyclohexane impurity in red, which comes out of as a Leakey component in column 4 and also a Leakey component in column 5. It must be separated from column 5 to purify styrene to specification, which is our second key component. As you can see, styrene is the light key component in column 4 and the heavy key component in column 5. A total of 100,000 pounds per hour are produced of styrene. As you can see, 50,000 pounds in column 5A and another 50,000 pounds in column 5B. The product styrene must be pumped to 50 psi and cooled to 50 degrees Fahrenheit for product storage. As you can also see, inhibitor is added into the stream to prevent styrene from polymerizing. Styrene polymerizes more at high temperatures, and throughout the process, it only polymerizes by 0.1%, mainly due to the reboiler temperature in column 5 being high. Our third main component in the distillation process is the benzaldehyde impurity, which is shown in green. Benzaldehyde comes in the bottom stream of column 4 and also is the likey component in column 6. Benzaldehyde must be separated from benzoic acid product, which is our next one in blue. Benzoic acid is the heavy key component in column 4 and column 6. Only a total of 1,500 pounds per hour of benzoic acid are produced as product. However, we found column 6 to still be feasible in our plant as the profits from 15,000 pounds per hour outweighs the utility of column 6. Now I'm going to let Nick talk about the costs of our plant.
So as you see here, we have the breakdown of our total capital cost of $888 million, and it's broken down into 5 main key components. First is the OBL, which was 39% of our total capital cost, and that consisted of the utilities that were used throughout the plant. The 20% of the total capital cost was the IBL, which was the actual unit operations we need for our plant. The escalation was 14% of our total capital cost, and that was 13% of our current capital estimate. And the contingency was 25% of our total capital cost and was 20% of our current point estimate and the escalation. And then this last 2% of our other was 4% of our total contractor costs. This is a breakdown of our costs throughout the plant for the materials. So this portion here is the utilities, which was used for cooling and heating streams throughout the process. This small purple piece here is for the labor, which is paying the actual workers in our plant. This light blue piece is our SG&A, which is our just general and administrative expenses. The darker blue piece is our fixed costs, which is our taxes, our overhead, and our insurance costs. And then our large portion is the raw materials, and that is mainly consisted of the raw feed and the acetonitrile use. Here's the cumulative cash flow summary over the course of our plant, and as you can see, it decreases, increases, and then decreases again. And the slight increase you see in the 3rd to 6th years is from the operating capacity increasing. But after we hit 100% operating capacity, the operating costs are too much and we just plummet. And now I'm going to hand it off to Shivam to talk about the sensitivity.
So we did sensitivity analysis on 2 different cases. The first one was the natural gas price. As you can see on the graph, the natural gas price rise over the years, and natural gas being one of the biggest utilities that we used, it would affect our capital cost and it would increase the numbers, and as we already have a loss, it would even increase the loss number. The other case that we took into account was the fixed cost. So this is the base case that we have for 32 operators and $85,000 per operator, and the alternate case that we used was the 15 operators with $70,000 per operators. The alternate case, the numbers that we used are not realistic and cannot be used in the real life, but also when considering these numbers, they do not make a big impact on the current loss or the capital cost that we have, so we could not even use the alternate case. Coming on to the PDRI, starting from the gate 3, everything that we did was accounted using the PDRI. So for the first in gate 3, the PDRI 1, we got a number of 673, which is a pretty high number, which is reasonable because we did not take most of the things into account during that point of time. For the second PDRI, we got a number of 492, which the number came down from the first PDRI as we took into account the equipment sizing and the site location and some other small things. Lastly, the final gate 5, we did PDRI 2I, which brought the number down to 404 as we did the final steps for our project and took into account the economic evaluation. This number is still high because a good PDRI score is less than 200, which is a perfect project, which includes everything, and everything is taken into consideration. Lastly, concluding our presentation, the plant that we came up with, the idea that we came up with, is not profitable at the current conditions, and we would need to make significant changes for us to move forward with the idea that we have. Thank you.